Welcome to today's lesson on correlation in statistics. Correlation is one of the most important concepts in statistics, as it helps us understand relationships between variables. Correlation measures the strength and direction of a linear relationship between two quantitative variables, which we typically denote as x and y. The most common measure of correlation is the Pearson correlation coefficient, which is denoted by the letter R. The formula for the Pearson correlation coefficient looks like this. R equals the sum of x sub I minus x bar times y sub I minus y bar, divided by the square root of the sum of x sub I minus x bar, squared times the square root of the sum of y sub I minus y bar, squared. Let's break down what this means. X sub I and y sub I are the individual data points. X bar and y bar are the sample means of x and y. N is the sample size. In essence, this formula measures how much x and y vary together, relative to how much they vary independently. Now, let's interpret what different values of R mean. R always falls between -1 and +1. Inclusive, when R is greater than 0, we have a positive linear association. This means that as x increases, y tends to increase as well. When R is less than 0, we have a negative linear association. This means that as x increases, y tends to decrease. The absolute value of R tells us the strength of the relationship. When the absolute value of R is close to 1, we have a strong linear relationship. When the absolute value of R is close to 0, we have a weak or no linear relationship. Let's go through an example to see how to calculate the correlation coefficient. Suppose we have this paired data: 1, 2, 2, 3, 3, 5, and 4, 4. Step 1. Calculate the means. X bar equals 1 plus 2 plus 3 plus 4 divided by 4, which equals 2.5. Y bar equals 2 plus 3 plus 5 plus 4 divided by 4, which equals 3.5. Step 2. Calculate the numerator and denominators. For the numerator, we compute the sum of x sub I minus x bar times y sub I minus y bar. Let's calculate each term. For the first point, 1 minus 2.5 times 2 minus 3.5 equals negative 1.5 times negative 1.5, which is 2.25. For the second point, 2 minus 2.5 times 3 minus 3.5 equals negative 0.5 times negative 0.5, which is 0.25. For the third point, 3 minus 2.5 times 5 minus 3.5 equals 0.5 times 1.5, which is 0.75. For the fourth point, 4 minus 2.5 times 4 minus 3.5 equals 1.5 times 0.5, which is 0.75. Adding these up, 2.25 plus 0.25 plus 0.75 plus 0.75 equals 4.0. Now for the denominator, we need the sum of x sub I minus x bar squared, which is 1 minus 2.5, superscript 2 plus 2 minus 2.5, superscript 2 plus 3 minus 2.5, superscript 2 plus 4 minus 2.5, superscript 2 equals 2.25 plus 0.25 plus 0.25 plus 2.25 equals 5.0. Similarly, the sum of y sub I minus y bar squared is 2 minus 3.5, superscript 2 plus 3 minus 3.5, superscript 2 plus 5 minus 3.5, superscript 2 plus 4 minus 3.5, superscript 2 equals 2.25 plus 0.25 plus 2.25 plus 0.25 equals 5.0. Now we can calculate R. R equals 4.0 divided by square root of 5.0 times square root of 5.0, which equals 4.0 divided by 5.0, which equals 0.8. With an R value of 0.8, we have a strong positive correlation between these variables, indicating that as x increases, y tends to increase as well. Once we've calculated the correlation coefficient, we may want to test whether it represents a significant relationship or just random chance. We typically test the null hypothesis H0 that rho equals 0, no population correlation, versus the alternative hypothesis HA, that rho is not equal to 0. To do this, we can use a t-test with the following test statistic. T equals R times the square root of n minus 2 divided by 1 minus R squared. This t-statistic follows a t-distribution with n minus 2 degrees of freedom. It's important to know that the Pearson correlation coefficient isn't the only measure of association between variables. Another common measure is Spearman's rho, which is rank-based and measures monotonic relationships rather than strictly linear ones. There's also Kendall's tau, which is another rank-based measure that's less sensitive to outliers and ties in the data. Remember that correlation measures linear relationships. Two variables might have a perfect, nonlinear relationship, but their Pearson correlation could be 0. Before we wrap up, let's address some common misconceptions about correlation. First, correlation does not imply causation. Just because two variables are correlated doesn't mean that one causes the other. There might be a third variable influencing both. Second, the magnitude of the correlation coefficient doesn't reflect the slope of the relationship. It only measures how closely the data points follow a straight line. Third, correlation is sensitive to outliers. A single extreme value can dramatically change the correlation coefficient. In conclusion, correlation is a powerful statistical tool that helps us understand relationships between variables. The Pearson correlation coefficient measures the strength and direction of linear relationships, with values ranging from -1 to +1. Remember that correlation only measures linear associations, doesn't imply causation, and can be affected by outliers. When analyzing data, correlation is often a good starting point, but it should be complemented with other analyses for a complete understanding of your data relationships.